All right, so our essential question, how are exponents and radicals used to represent roots of real numbers? We're going to answer that question right now, starting with example number 1. All right, so let's talk about some cube roots and square roots, right? So there are some numbers that you should essentially have kind of committed to memory. And these numbers are your perfect squares and perfect cubes. So numbers that are perfect squares are 4, 9, 16, 25, right? And we go all the way up. I'm just going to go ahead, and well, maybe I won't write them. These ones are simple. And you should note, 4, 9, 16, 25, 36, 49, 80, 64. I missed one. All right, 64, 81. You should be able to go up to, 12, 13. That's when people, start to forget. Now, the ones these are probably fairly familiar to you, right? Or very familiar. Something that you probably don't deal with are going to be perfect cubes. Right, so these are numbers that if you multiply the same number by itself 3 times, right, you'll get this number. That's what a perfect cube is. So let's go through it, right? 2 times 2 times 2 is 8. So our first perfect cube, 1, of course, is 1, right? They're all, but I don't know. I feel like my number theory professor would have been mad if I included that one. So, all right. But it does work, right? Because 1 times 1 is 1, and 1 times 1 times 1 is 1. It just doesn't really count because it doesn't have a unique prime factorization. Anyhow, sorry. So 2 times 2 times 2, 3 times 3 times 3 is 27. 4 times 4 times 4, 64. 5 times 5 times 5. I don't think you'll ever get 6, right? So perfect cubes, the ones that you have to have memorized, there aren't many of them. Okay. So this question is asking, what are all the real cube roots of 125? In other words, it's saying, what is that? And because 125 is 5 times 5 times 5, your answer is 5, right? And I'll just write because 5 times 5 times 5 is equal to 125. Yes, so this is why. Okay, let's do another one. Oh, I can never get that button because of my focus. All right, so what are all the real fourth roots of 16? So another thing that you're going to kind of need to have in the back of your mind are going to be multiples of 2, or not multiples, but keep in mind that we go that 2 to the 3rd power is 8, 2 to the 4th power, so powers of 2. So it's something else to note, powers of 2. Okay, so you just do 16. You just keep doubling these things, right? So 2 to the 5th is 32, and 2 to the 6th is 64. sometimes, nah, I don't think you'll usually get problems that'll just assume that you understand that the sixth root of 64 is 2, right? And I just want to point that out. What does that say? That means that the sixth root of 64 is 2. It's kind of what that's pointing out to. So if you want to know the fourth root of 16, well, it turns out that 2 to the fourth power is 16. So that means the fourth root of 16 is 2. And you'll deal with that quite a bit. So really, kind of the arithmetic type information that you need for what we're going to be doing, dealing with radicals and rational exponents, is you got to know your perfect squares, you got to know your perfect cubes, and then these powers of 2. Having those tools, if you will, in your tool belt will help you get stumped less often. All right. Okay. I think that's it. All right, so let's move on and start talking about rational exponents. That's the one we want. Okay, so I'm going to introduce a rule to you before we get started. And that is that if I have some nth root of a, right, we can write that as a to the 1 over n power. So we can write a radical in terms of an exponent. Another kind of variation of this is that if I have some nth root of a to the m power, that's going to be a to the m over n power. Strangely enough, also, if I have some nth root of a to the m, that is also going to be a to the m over n. Just some rules that we're going to be using. All right, so let's apply that stuff to this particular problem. So what does that mean? That means that this guy must be a, right? And then this must be n, 4, right? So it looks like we have, we're going from here to here on our first formula that we have there. So all we got to do is plug that stuff in, right? If that's 4, then I can write that, right? I'll write my radical. My 4 goes here, and my 16 goes there. I just, for some reason, I just can't say this question without putting it in like an English voice, like an angry English voice. What is the meaning of it? Sorry. Anyways. Probably too early for that nonsense. Let's do another one. Let's do another one. It looks like for this one, we're going to be using the fact that some a to the some nth root of a to the m is equal to a to the m over n. Just remember, this guy is always on the bottom. Just can't catch a break. Okay. N is always going to be in the bottom of, that rational exponent there. Okay, so then in that case, it must be the case that A is 27, right? So this means that A is 27, if we're going to put it in there, right? And then M is 2, and N is 3, and all we got to do is plug that stuff in there, right? So I'll say that 27 to the 2/3 power is going to be equal to a root. I know 27 is going to go in there, and the 3 is going to go in there, and the 2 there. I just want to go ahead and work this thing out, right? And it's kind of cool to look at this, that to say that these things are, this is also the same, right? Remember I said that you could call this the third, oh, sorry, let's use the things, right? We said this was A to the M. So then we can actually simplify this. This is not what the book wants us to do, but I'm gonna do it anyways. You could also put that thing in your handy dandy calculator, right? It will spit out an answer for you. In fact, let's go ahead and do that. And then I'm gonna, well, first let's do this. Let's complete the problem. Let's go. I want to write it like that. It's gonna be easier. You could square the 27 and then take the cube root. But if you're gonna do that in your head, I don't really want to multiply 27 times 27. I do know that there's a number that when I multiply it times itself 3 times, it's 27. That number is 3. So the cube root of 27 is 3. So then I get a much easier, it's just easier to do in my head that way. But let's go ahead and get out our handy dandy calculators and let's see how we enter these things if you needed to. Okay. So, I was calculating the cube root of 3 in our last, or the square root of 3. Okay. So, there is a cool thing in here if you hit math. You can do a cube root or you can do anyone. So I'm going to show you anyone. We'll put the 3 in there. But the one with the X on it, you can do a 4th root, a 5th root, any root that you would like. So I'm just going to do that one. In this case, it's the 3rd root of 27 to the 2nd power. And we hit enter and get 9. And just kind of interestingly enough, for some reason, when I learn about math rules, for instance, the one that we were just talking about where, you can pull that square to the outside, that to me is just like, why? I'm like, huh? So for me, I have this weird thing I have to do. I have to check it with the calculator and make sure that it's the same. We did the arithmetic, but honestly, this is something that I did when I was learning math a lot, was check rules in the calculator. And for some reason, they made more sense to me, right? If I just put numbers in and I saw it actually worked with real numbers, then I could believe that it worked for some sort of variable expression, which is what we're going to be getting into. So, but I'm going to show you how to do that again. Remember, we went down, we'll go down to the one with the X, 3, 27. So this is just an example of checking this rule using your calculator. And it turns out that those two expressions are exactly the same because when I hit enter on my calculator, they calculate the exact same number. And I don't know, for some reason that to me Just helps me make sense of everything. So there you go. There that is. Okay. Wow, that was weird. But cool. Okay. Let's go ahead and simplify some n3s. Okay, here we go. So we're going to simplify this expression. We're going to use those rules that I wrote on the two previous questions, right, with the A to the M to the N and all that stuff. So on this one, that is a 5. So I'm going to do a couple things, okay? So there's another rule. It tells me that if I have some nth root of A times B, I can write this as the nth root of A times the nth root of B. And that's how I'm going to approach this thing. So if I have a product underneath a radical, I need to do this. This is what I have to do. And I do indeed have a product, right? Because I could write this as the fifth root of poop. That 5 is terrible. I could write this as the fifth root of 32. Goodness gracious. 32 times m to the 15, right? And thus I would write it as the fifth root using my rule that I have over there on the right. 32 times the fifth root of m to the 15th. And goodness gracious, it's not happening well for me to watch. I think that if that might help things. What? You. Oh. Okay then. That's too skinny. Sorry guys. Probably shouldn't have done that. All right. So what is the fifth root of 32? Remember I told you about those powers of 2? It's 2. And you can put that in your handy dandy calculator, right? Why is the fifth root of 32 2? Because 2 times 2 times 2 times 2 times 2 is 32. Let's go ahead and write this one as a rational exponent. So this is m to the 15 over 5 power. And we can simplify that as well, right? So that's 2m to the third power. And there we go. We have simplified it. Okay. None of these. Sorry. All right. Let's move. No stuff here. Okay. All right. So now we're going to do some solving. So this is when we're really getting down to the nitty gritty on this thing. Let's solve an expression where we're going to have to take some sort of larger root. So the first thing that we need to do with this is get this x to the fifth all by itself. I'm just going to rewrite the equation here. Oh, I should probably rewrite it correctly. I used to have a professor I'm going to divide both sides by 2. Physics professor that was so hard on himself. Anytime he would make a mistake, someone would point it out. They'd be like, yeah, professor, I think that's supposed to be a minus sign. You'd look at the problem, you'd turn around, you'd look at the person, and then he'd just start screaming and hitting the board. He'd be like, I'm stupid! I'm stupid! That was the weirdest thing to watch. It was awesome at the same time. Because that was kind of a boring class. All right, sorry. Sorry, physics wasn't a boring class. It was only boring because I had to take it and I'd already taken advanced physics and I had to take an intro to physics class. So I just sat in the back and waited for that guy to freak out. It was awesome. All right, so I need to get rid of that x to the 5th. So what I'm going to do is I'm going to take the 5th root of both sides. Just like if it was a square, we would take the square root of both sides. All right, so it turns out the 5th root of 5, I'm actually going to do something interesting. I'm going to go ahead and use that rule just to show you why those cancel, right? That if I have some a to the, if I have some nth root of a to the m, it's equal to a to the m over n power. I'm just going to write that here, just because it's interesting to see, right? If I write that in that way, this is x to the 5/5 power. And we just learned that the 5th root of 32 is 2. So that's x to the 1st power, right? So then we can say that x is 2. I really liked this. When I finally saw this, I was like, oh, well, that's why you take the square root of both sides, right? That's why a square root undoes something squared, right? Because and it's just so nice that it works that way with rational. Oh, not that one. This one. Yeah. Let's do another one of these, and then I think I want to double back and do another example of simplifying. Now that I've done the lesson, I feel like it's lacking right there. So let's go ahead and solve a couple of these, and then we'll find some more expressions to simplify. I like that one. I hope it copies the whole thing. Let's do this over here. I think it just looks nicer. Fantastic. Let's solve this one. All right, so the first thing I want to do is divide both sides by 5 to get rid of that 5, that coefficient there. So I get that x cubed is equal to, let's see, 5 goes into 32, 6 times 2, 4, 64. Right, that's a 2 there. So the shorthand way of doing division. All right, hey, something times itself 3 times is 64. Remember from that list of perfect cubes, we know that that must be 4. Sorry, I don't know why I just skipped that just for friends, right? Let's take the cube root of both sides. Sorry. And then you know that the cube root of cube is 1, or it just gets rid of your cube. And then the cube root of 64 is, right? Because 4 times 4 times 4 is. So there you go. Let's go ahead and do an example, another simplifying example. Really not feeling great about only having one example for that now that we're done. So let me work on the fly real quick And I think the deal is the reason why there aren't as many is because we are going to avoid giving you all problems that have two variables in them. And I don't see anything, so it's okay. I can make one up. All right, so let's simplify. The sixth root of I mean, I guess, I'm sorry, I don't know if I want to use the sixth root or not. Didn't we? Yeah, we'll just do it. All right, let's simplify that. So the first thing we need to do is separate it. Right, so we can write that as the sixth root of 64 times the sixth root of x squared, x to the 12th power. All right, the sixth root of 64 is 2. And let's go ahead and write this as a rational exponent. So that's going to be 12 over 6. So that's going to give me 2x squared. Let's do another one. So this would be, I don't know, I think this is now b. And let's get c out. So let's do the third root of 125 y to the 9th power. All right. So we'll separate it. And that's going to be the cube root of 125 times the cube root of y to the 9th power. It turns out that 5 times 5 times 5 is 125. So the cube root of 125 is 5. And then this is y to the 9/3 power, or 5y cubed. Well, all right. So that was nice to get a couple more in there, I think. Cool.